This is going to be the lecture over the PowerPoints here for Chapter 2. We're going to be talking about nuclear transformations. What does that mean for you in radiation therapy? So let's take a look here at radioactivity, discovered in 1896 by Henry Becquerel. Radiation is given off by the nuclei of the elements. I wasn't really sure, of course, at the time what the mechanism was for that. So over the years, we come to determine what it is that's causing that specifically. Radiation can be in the form of particles or electromagnetic radiation, and it can be both, just to give you even more confused. So what are some characteristics here of radioactivity? Radioactivity results when unstable nuclei attempt to minimize their energy. In other words, become more tightly bound to an atom. This is an attempt, when you see something like this happen, generally what you're looking to do is to make the situation more stable from the point of view of energy. So the parent nucleus undergoes some sort of spontaneous transformation into a daughter nucleus. How is that done? We've got three different methods here. You've got gamma rays, you've got alpha particles, and you've got beta particles. This would be a gamma. It's not usually represented with Y, but gamma, usually when you see that, let's see if I can draw that here. Irritate this and this. It's going to look more along the lines of something like Greek letter gamma. So protons and neutrons are generally not spontaneously emitted from the nuclei. So you've got all three of these types of radiations emitted by radium. So let's say you've got the radium encapsulated in some sort of box here. And then what you see is coming out here. You have alpha particles, you have beta particles, and then you have gamma particles. So radioactive decay. This is characteristic of the type of atoms and changes from one nuclide to the next. So usually the probability of decay per unit time for a particular radioisotope is going to be measured rather than calculated. So units are time raised to the -1 power. So you have your parent nuclide, and then you have the daughter nuclide, and then you can see the transformation there. So what you're going to need to know is the number of nuclei X, a number of nuclei X at any given time. This is going to be a function of time. So the expectation is that you're going to start out with some initial number of nuclei, n sub naught. And that number decreases with time until after some long period of time, there's absolutely no nuclei left. In other words, it turns into 0. If we know the number of nuclei initially present at t is equal to 0, then n at t is equal to 0 is equal to n naught. So radioactive decay. We got 2 samples of a radionuclide, with one sample having twice as many nuclei as the other. The number of decays per second will be twice as large as the larger sample. So the number of decays per second is proportional to the number of nuclei present in the sample. So one way that is usually written, let's see if I can get this going here. And you may have seen this at some point. of n. But if we're not looking at the calculus, we're just looking at just discussing things with change, usually the delta is what's used. So it's the rate of change of n, or the change of n, the change in time. For anybody who has had calculus, you recognize that. So it looks like we're having some problems here with the formatting in these slides. Let's see here. Okay, rather than depend on the slides, which apparently are having some difficulty exhibiting what it is that we're trying to, what I'm trying to illustrate, let's go through and let's take a look at the book here, and let's see what it's talking about. It's describing here that it is not possible to know when a particular atom will disintegrate. It's really more of a question of probability, will it or won't it? So what you can do is accurately predict in a large collection of atoms the proportion that will disintegrate in a given amount of time. So the simple fact here that we have a change in the number of atoms per unit time, which is delta N over delta T, and that's going to be proportional to the number of radioactive atoms. In other words, this change in the number with respect to time that go through this radioactive decay is going to be proportional to the number that are present. We know it's proportional. We're not exactly sure how to make this an equation. How do you make it exact? The way you do that is you slap a coefficient in front of this, and you're going to make it negative. So this is going to be the change in the number with respect to time, and we're going to say that's equal to minus some number, we don't know exactly what it is, times m. That changes it from being proportional to being exact, to being an equation. This lambda value, this coefficient that we throw in there, is a constant, and it's going to be called the decay constant. And the minus sign is going to indicate that the number of radioactive atoms present decreases with time. In other words, you don't have anything replacing it. So whatever you start out with, you're going to constantly have less of as you go along. If the change in N and the change in T are so small that they can be replaced by differentials, if you're getting, again, stepping into the calculus frame, we're going to make these smaller and smaller and smaller. This becomes a differential equation. Now, don't worry so much about trying to work with solving a differential equation. All I really want you to know is that this particular relationship comes about. We're not going to worry about how we get there. We just get here. So the number you have at any given time is going to be equal to the number you start with times this function, which involves not only time, but also the decay constant. And that number here is actually called E. That is approximately equal to 2.718. You should have it in your calculator, something that you can call up, and you're going to need it for this particular set of problems. So now let's head on back. So what can we say about lambda here, this decay constant? Well, the larger the value, the more rapid the decay. So units of lambda are 1 over time, expressed in whatever units of time are convenient, such as seconds, hours, years, all raised to the -1 power. So for lambda, the decay constant can be thought of as a fractional amount of decay per unit time for small fractional decay. Again, this is where this function comes into play. It gives the expected behavior for time is equal to 0. If you were to substitute in 0 into this equation, 0 multiplied by the decay constant is going to give you a 0 here in the exponent. Anything raised to the 0 power, any non-zero number raised to the 0 power is going to end up being 1. So this term right here falls away, because it becomes 1. So the original number you start with times 1 is going to be equal to the original number you start with. And as t approaches what should be infinity, and let me write that out here. Then n is going to approach 0. So n, of course, is going to be the number of radioactive atoms remaining after a certain amount of time. N sub naught is the number that you started with. Okay. So the number of decays per second is going to be called the activity. And let's go back here and let's see if we've got, yeah, let's see if I can move this out of the way. There we go. So the number of disintegrations per unit time is going to be referred to as the activity. If basically you go through this relationship right here and you replace this with A, then what you come to find out here is that the activity is going to be equal to the positive decay constant times n. And the negative sign has been left off because activity is the disintegration rate rather than change in number of atoms. In other words, this is going to be something that will be directly proportional to the number of atoms that you've got there, but not in a negative sense. In other words, the more atoms you have, the more activity you should have. So if you go through the same process, which I have not spelled out here for you, but if you do go through the same process here with activity, like you did with a number of atoms, this is the equation that you come up with. Now, A sub naught is going to be the original activity. And as it turns out here, it's going to be equal to lambda times n sub naught. Now, the SI unit for activity is going to be the becquerel. In radiation therapy, a more common unit that we run across is going to be the curie. So this is going to be defined as 1 curie is equal to 3.7 times 10 to the 10th becquerels. That'll be an important conversion going forward. If you start hacking away at the number of curies you have by, saying milli, micro, nano, pico, you can see how many curies you end up with. And guess what? As you start to split this, then this number here, or this number here, comes down to 7 to 4 to 1 to -2. So, and a becquerel is basically going to be one decay, the decay of one atom per second. So unit of activity here. Okay, so 1 megabecquerel is going to be equal to 10 to the 6th decays per second. Okay, so let's talk a little bit about half-life here. All right, half-life is going to be the time required for either the activity or the number of radioactive atoms to decay to half the original value. Now, through some mathematics, we find out that the half-life here is going to be equal to 0.693 divided by the decay constant. As you can see here, those two are inversely related. So if we take a look at the relationship here between these two, when t is equal to this and when lambda is equal to 1/2, if we go through here and make some substitutions, we can take lambda is equal to 1/2, or when t is equal to this, there we go, and when that is equal to 1/2, what we see here, okay, so we know that this is equal to 1/2 of what we started with. We know this. Okay, we don't have that quite just yet, but we do know this. We go through, if we divide both sides here by the initial activity, find out the 1/2 is equal to e to the minus lambda, because we don't yet know what it is. And we take the natural log of both sides, taking the natural log of this. Then what we find out here is natural log of 1 minus natural log of 2 using the property of logs is going to be equal to lambda times this. Down here a little bit, then we see that this times this is equal to minus this. And therefore, solving for this, we end up with the negatives canceling. And finally, we end up with oops. This. And that actually might be something here. You can see that here in the book as well. If you take the natural log of 2, that ends up being 0.693 and ends up with this particular relationship. So again, after 1 half-life, the activity of the radioisotope will be 1/2 of the original activity. After 2 half-lives, the activity will be 1/2 raised to the second power, or 1/4 of the original activity. And after n, it'll be 1/2 raised to the n power. So you can see here, after n half-lives, it's basically the same thing as taking the original activity times 0.5 raised to the n, where n is equal to t, small t divided by the half-life. And that's going to end up being the number of half-lives. So we can see here a general decay curve where the activity as a percentage of the initial activity is plotted against time in units. If you plot this on a linear graph, you end up with a bow, just simply because you have a activity that is going to be relative or related to how much of the substance you have. As the substance starts to decay, it starts to get smaller and smaller. Over here, it is linear. And what you notice about that is that this is a semi-logarithmic graph, which means the spacing up here, as you go from 10 to 20 to 30 to 40, 50, 60, up to 100, it is taking the log of one side and relating it to just an absolute measurement of the other. And because of that, that straightens out the relationship into a line. So we're going to run across some problems here. I am going to be working a lot of these particular problems in separate videos, so I just want you to be aware of that. Okay, so the average lifetime for the decay of radioactive atoms is actually going to be, and again, we've got formatting problems here. So let's see if we can find better representation here. Okay, so let's back up. Okay, so a source to provide the same total number of disintegrations in time as the given source decaying exponentially from here. The initial activity. Imaginary source would produce a total number of disintegrations. Also, because the total number of disintegrations must be equal to n naught, we must have this. In other words, if we take the total number of disintegrations, multiply that by lambda, multiplying it by this, we should end up with this. Therefore, the average lifetime is going to end up being 1 over lambda. So the average lifetime is going to end up being 1.44 times the half-life of that particular situation, whatever that isotope or whatever that element is that we're dealing with. You do have some problems here that are worked out. I will also be doing some a little bit later on. I would encourage you to read through these, but I will post some separate videos of those. So the mean life or average life, we've already discussed that a little bit. So we've got the mean life, and we've got average lifetime, which should end up being pretty much, yeah, that's the same thing. Okay. Activity per unit mass of a radionuclide is going to be defined as specific activity. High specific activity is advantageous for use of elements as tracers in studying biochemical processes. In other words, you want to be able to see things and see things fairly quickly. Use of radioisotopes as teletherapy sources. So again, these are going to relate to the problems that are in the book, and I will work through some of those a little bit later so we can keep the size of this particular video a little shorter. So here we have a decay series, and what you're seeing here is the beginning of it and then tracing it through its several steps, and then knowing how it can decay into something that is stable. In this particular series, you're going from uranium down to lead. So all naturally occurring radioactive elements have been grouped into 3 series. You've got the uranium series, you've got the actinium, and then you've got the thorium. So this originates with uranium-238, having a half-life of a very long time, and goes through a series of transformations involving the emissions of alpha and beta particles. So you can see part of the transition starting up here and then ending up with lead, just like what we saw on that chart. So the gamma rays are also produced as a result of some of these transformations. So it starts from uranium. This is the actinium series. What we had up here was the uranium series. The actinium series starts from uranium-235. Difference here is that we started with 238. Here, we start with uranium-235 and end up with lead. Here we ended up with lead, but we ended up with lead-206 as opposed to lead-207. You can also see here that the half-life shorter than what we saw up here. So the Thorium series. This begins with thorium-232 with its half-life of 1.39 times 10 to the 10 years. That's a lot of years. So all the series terminate at the stable isotopes of lead with mass numbers 206, 207, and 208, respectively. So here we end up with, started with thorium, we ended up with lead 208. Here we ended up with lead 207 and the actinium series, and here we ended up with 206 in the uranium series. Now, charts of a decay scheme. So here we have cobalt-60, and we can see there's a beta minus decay. We can see what the probability is of that and what the energy release happens to be out of this. Here we have another beta minus decay, which happens far more often. And you can see the energy that's released here. So when you have these particular steps that are going on here, then you can see the beta minus decay can give you two different possibilities. Now, when it decays to this particular point, you're looking at an energy level of 2.5. When it gets to this point, you're looking at an energy level of 1.33. Now, since you have a decay here that happens 0.1% of the time that falls to this particular energy level, and then you're seeing a gamma emission, which releases 1.33 MeV, finally decaying to nickel, you're always, and you have another pathway here, this being far more probable. You're going to see the beta minus decay, and then you're going to see a gamma emission of 1.17, and then eventually a 1.33. No matter which path that you take here, you're always going to see this emission. Most of the time, you're also going to see this as well. This is why sometimes when you take both of those two and you average them together, and they ask you what the energy release is from cobalt-60, sometimes people will say 1.25 MeV, because it's an average of both of these. But what you're really seeing here is you're seeing two different schemes of decay from cobalt-60 with its half-life given here. You're always going to see this most of the time, 99% or more of the time. You're also going to see this as well. So a description of radioactive decay in which energy is depicted on the vertical, the y-axis, and the atomic number is shown on the horizontal, or the x-axis. The original nuclide, the parent, is depicted as X, and the product nuclide is denoted as elements depending on the decay path. So many radioactive nuclides undergo successive transformations in which the original nuclide, called the parent, gives rise to a radioactive parent nuclide called the daughter. So when I think I should have said radioactive product nuclide. I don't think I said that. So the parent is what is decaying. The product is or the daughter is what you end up with. So when half-life of the parent is longer than the daughter, equilibrium is achieved over a period of time. Transient equilibrium is what happens if the half-life of the parent is not much longer than that of the daughter. So here is an example. You've got transient equilibrium, you've got technetium, which is metastable, and then you have molybdenum running along right here. Now this is a case of transient equilibrium. And let's see if the book has a illustration of that. Okay, so you've got the parent, the molybdenum, which has a half-life of 67 hours, and then you have the daughter, which is the technetium, of 6 hours. Relatively speaking, they're considering this to be not that much longer than what you have with the daughter. So you have secular equilibrium showing, this is transient equilibrium, sorry, we don't want to get on to another case. So you've got the activity here where you start off with 100% of whatever activity you had here for the molybdenum. You go down here to the half-life of about 67 hours, which is roughly right here. That should be about half of the activity left, since that's proportional to what's there. In that particular amount of time, you can see the decay going there. And then if you continue on for a little while longer, if you got up to 132 hours, you'd see it fall to 0.25. For the relative activity here of the daughter product, the technetium, you can see it rise. And because this is decaying into this, so you can see the rise there. And then eventually, as this has decayed, this starts to run parallel to the other because this is not making as much of the technetium as it used to. And this is decaying faster. So this is the result that you see. Radium here, on the other hand, this is what happens when the secular equilibrium is what happens if the half-life of the parent is much longer than that of the daughter. So you got the radium here, and then it's decaying into radon. So the radium, you're looking at, 1,622 years. Radon has a half-life of 3.8 days. Not very long, certainly compared to this. So what you're seeing here is the relative activity here. As this decays, this relative activity of the daughter product eventually comes up and approximates the same activity as the radium. All right, so alpha particle decay. Alpha particle decay, you've got radioactive nuclides with very high atomic numbers. That's where you're going to see this. The unstable nucleus is going to emit a particle composed of 2 protons and 2 neutrons. The particle is going to be basically the nucleus of a helium atom. The atomic number of the nucleus is reduced by 2, and the mass number is reduced by 4, because basically you're pulling out 4 nucleons, 2 of which are protons. So you've got the parent product, or the parent atom here. You have the daughter product, whatever that atom happens to be, plus a helium nucleus. Helium, this is going to represent the alpha particle. The sum of the mass numbers and the sum of the atomic numbers after the transition equal the mass and the atomic numbers of the parent. Energy is going to be released as kinetic energy of the alpha particle. So sometimes followed by energy released during an isomeric transition, resulting in emission of a gamma ray or conversion electron. Alpha particles are always ejected with energy characteristics of the particular nuclear transition. Now for beta particle decay. The process of radioactive decay in which it is accompanied by the ejection of a positive or a negative electron from the nucleus. Yeah, those things can shoot out from the nucleus. Negative E, or the negatron, is denoted by, well, this. And the positive, or the positron, is, let's see if we can find. There we go. this is having some real problems with the Greek symbols. So, whoops, didn't mean for that to happen. And I still don't know why that's happening. Okay. I would really prefer that this go away. Let's see. No, I'm really not interested in seeing more. Thank you. There we go. Okay, so the negative electron or negatron is denoted with beta minus. And the positive electron or positron is with the beta positive. Neither of these particles exist as you see them inside the nucleus, but they're created at the instant of the decay process. So the basic transformations are written in this format. You've got a neutron that ends up being converted into a proton. In order to conserve charge, you can't just have charge created out of nothing. You have to let that go somewhere. And that happens when this negatron or negative electron, seems redundant, but there we are, is created. There's also a neutrino that goes along with this. That's your beta minus decay. For a proton that ends up converting into a neutron, again, you've taken away the charge. So you got to give it to something. It's got to be conserved somehow. So it gets put on this electron that is not negative, but positive. And that ends up becoming a beta positive decay, beta plus decay. This little symbol here is going to stand for the antineutrino, and this is going to stand for a neutrino. Okay, so again, you can see here what we've got going on for a beta positive, beta particle decay. Neutron is transformed into a proton. The Z of the nucleus is increased by 1 with no change in the mass number. So the neutron to proton ratio is going to be reduced because you've increased this and you've taken away one of these, and the product nucleus is nearer the line of stability. Remember the line where you have n divided by z, it's drawn like this. The closer you are to that particular line, the closer you are to having a stable nucleus. A negatron is going to be ejected from the nucleus together with a neutrino that carries away the remainder of the released energy. So if we look here at the relative number of particles per unit energy interval, we can see a graph here. We can see the maximum here, 1.71, average here of 0.69 MeV. It would be nice to have some context on that. Let's see. Here we go. That is the beta ray energy spectrum for phosphorus 32. So in other words, these are the rays and the energies that you would see from that particular type of decay. So let's see if we can find a better description here of the decay of well, I guess they don't have it. Okay. Thought they might want to have one here for cobalt and nickel, but sadly, I do not see that. So going from cobalt to nickel, we have an isomeric transition that is often accompanied by the release of cascading gamma rays of 1.7 and 1.33 MeV. It's just like the picture that we saw earlier. Here. where you've got these two specific decays going on in a beta minus decay. So here we have a situation where we have a positive beta plus decay. So positron emitting nuclides are going to have a deficit of neutrons, and their NP ratios are lower than that of a stable nuclei. So for these nuclides to achieve stability, the decay mode must result in an increase in this ratio. So you can do that by having a beta decay involving the emission of a positive electron or a positron. And this is going to be the overall decay scheme. So if you take sodium and watch it decay into neon, and you can see the half-life here, 2.6 days. You can see here that you end up getting a positron out of it. You've got a neutrino and you've got a release of energy. So that release of energy is the sum of the maximum kinetic energy of the positron and the energies of the gamma rays. So you've got an energy level diagram here of sodium. So you can see here that you can have a beta plus decay this way. You can also have a beta plus decay this way. You're seeing that this happens 0.05% of the time. This happens 90% of the time. And the electron capture is another method of decay. And you see that about 10% of the time. If you take either one of these two paths, you end up here, you see a gamma release, and then you end up with neon 22. If you follow this specific path, you're seeing a maximum electron emission of 1.83 MeV, and that is something that's not very common. And you can see here with those percentages. So for those of you that might have some sort of connection to nuclear medicine, the phenomenon here of positron electron annihilation, it's got a practical use. It's used in PET. The isotopes such as fluoride or fluorine, I think fluorine 18, incorporated into a metabolically active compound, and it emits positrons, which are annihilated by electrons in the body tissues. For each of those annihilations, 2 photons are emitted in opposite directions. When you detect those photons with a ring of detectors that spin around the patient, the site of annihilation events and the intervening anatomy are reconstructed. And that's basically, you scan through once to get a picture of the anatomy, and then you can scan through again to see where those collisions are happening. You put the two together, and then you can see where the tumor lies. And that information comes in real handy whenever you're trying to plan, whenever you're trying to determine where it is in the body that the active sites of sugar uptake are happening. So this is one way in which, yes, we actually do use this stuff. Now let's go on. I think we'll talk about, let's see, this is negatron emission. We discussed that out of the book. We discussed positron emission and something that doesn't quite have all that crazy stuff going on there. We talked about positrons being emitted, combining with another a negatron, producing annihilation of the 2 particles, or perhaps just an electron. And then you have the 2 gamma ray photons being emitted. So we've seen all of these discussions here. Now, let's go on to electron capture. Oops. Electron capture is when one of the orbital electrons is captured by the nucleus. It involves mostly the K shell due to its closeness to the to the nucleus. In other words, if a nucleus is going to reach out and try to stabilize itself, what's going to be the easiest way to do it? Is it going to grab an electron from the outer rings, or would it try to grab one that is closer inside? And the answer is, of course, it's going to grab one that's closer in, and that's going to correspond to the K shell. So that's where this is coming from. So again, the book there doesn't, or the slides don't really show what's going on here. So you've got a proton inside the nucleus, grabs an electron out of the K shell, ends up neutralizing the charge. So the charge ends up producing a neutron, and then you've got a neutrino that starts running wild. The general equation is going to be that you've got your parent product here, captures an electron, you end up with some sort of a Z-1 atom here with a neutrino and a release of energy. This is an alternative to the positron decay, because what you're attempting to do here is you're attempting to change a proton into a neutron. What did we see before? Let's see if I can scroll back a little bit. We have a proton here turning into a neutron in order to try to get a balance between the number of neutrons and the number of protons that you have in the nucleus. And because of that, when that neutralizes, then you end up having the positron being emitted. This is another way to go about trying to get rid of the excess proton charge that you have in the nucleus. Process is referred to as the Decay capture. It can happen in the other shells. It's just usually far more common to have it happen here. That decay is going to create an empty hole in the involved shell that's going to be filled with an outer orbit electron. And that's going to give rise to characteristic X-rays. There's also going to be an emission of Auger electrons, which are monoenergetic electrons produced by the absorption of characteristic X-rays by the atom, and re-emission of the energy in the form of orbital electrons ejected from the atom. So it's crudely described as the internal photoelectric effect produced by the interaction of the electron capture characteristic X-rays with the same atom. Another name for characteristic X-rays produced by the interaction of photons with the atom is fluorescent X-rays. The excess energy released by the atom through electron transition from an outer orbit into the inner orbit appears as photons, or Auger electrons. And these are competing. Probability of fluorescent X-ray emission versus Auger electrons depends on the atomic number involved. Fluorescent yield, defined as the ratio of the number of characteristic photons emitted to the number of electron shell vacancies, increases with increasing atomic number. So for large Z values, fluorescent radiation is favored, while for lower Z values, Auger electrons are more probable. So for example, Auger electrons are emitted more frequently in materials of a Z less than 30, while fluorescent yield predominates for higher Z. For soft tissue, fluorescent yield is close to 0. For tungsten, it's the dominant process. Okay, so this talks about the Auger electrons. Okay. Electron captures do not yield a mass imbalance before and after the transition. There's no transition energy prerequisite. Positron decay occurs more frequently than electron capture for nuclei that can decay by either process. Internal conversion is a mode by which a nucleus left in an excited state after a nuclear transformation gets rid of excess energy. The excess nuclear energy is passed on to one of the orbital electrons, which is then ejected from the atom. So you've got the energy of conversion electrons from K shell. So you've got this going on here. So you've got a beta minus particle coming out. Let's see if we can. Here. So from left to right, the nucleus undergoes beta minus decay and creates a daughter nucleus, which is still in the excited state and decays by gamma emission. So that's what you've got going from here to here. You had a beta minus, which meant that you had an increase in the proton at the expense of a neutron. And so you've got this excited state, so it wants to kick out a gamma emission. That gamma ray could be absorbed by the atom. If it is absorbed by the atom, like this little electron dude here, it ejects that electron and it creates a vacancy here, which ends up needing to be filled. So in order to fill it, you've got to be able to have one of these out here want to jump, and that's easy to do from these shells, the L shell or the M shell, and jump down here into the K shell. When that happens, you see a characteristic X-ray being released. Another possibility here is you've got the ejection of an Auger electron, say from the M shell, with the difference in energy, K to L, and then also subtracting that out as well. So this level as well as the level from here to here. That's what this is trying to describe here. Isomeric transition. So when the excited state of the nucleus persists for an appreciable time, the excited nucleus exists in metastable state. That is an isomer of a final product nucleus. So in other words, technetium-99, technetium-99. Or gamma emission. An isomeric transition can occur by either of these two processes. Gamma rays are emitted during transitions between isomeric energy states of the nucleus. So in most radioactive transformations, the daughter nucleus loses the excess energy immediately in the form of gamma rays or by internal conversion. No radionuclide, however, decays solely by gamma emission. In the case of some nuclides, the excited state of the nucleus persists for an appreciable time. In that case, the excited nucleus is said to be in the metastable state, and that is an isomer of the final product, which is kind of what we just went over here. Okay, nuclear reactions. Okay, nuclear reactions. So the first nuclear reaction was observed by Rutherford in 1919. So he took nitrogen gas and bombarded it with alpha particles from a radioactive source. Sounds like something fun you'd do in your spare time. Let's take a look here again. The original transmutation reaction, written as you've got your nitrogen here, you've got the helium nucleus coming in, and then you've changed it into oxygen here with hydrogen, and then a little bit of energy. So what you're looking at here is the energy is released or absorbed depending on what's going on here during a nuclear reaction. If it's positive, energy has been released, and it's called exoergic. And if it is negative, energy has been absorbed and therefore is endoergic. Q is also nuclear reaction energy or disintegration energy, and is equal to the difference in the masses of the initial and the final particles. So if you go through, you know what the masses are of the particles that you put in, come up with a sum. You know what the mass of the particles are when you get out. This is what you got. You notice here that you end up missing a little bit of energy. So you've got something that's endoergic. So in other words, it's going to take at least 1.19 MeV of energy for that reaction to take place. It won't happen naturally. You've got to supply it somehow. The minimum required energy is called the threshold energy, and it must be available from the kinetic energy of the bombarding particle. So a reaction in which an alpha particle interacts with the nucleus to form a compound nucleus, which then disintegrates into a new nucleus by the ejection of a proton, is going to be an alpha proton reaction. So the first letter stands for the bombarding particle. In other words, this is what you got coming in. And the second is going to stand for the ejected particle, in this case, a proton. And then that's how it gets written. So a simpler notation is usually with, what you're starting with, what element, then you write the type of reaction, the alpha and the proton, and then you end up writing the final product. You don't have to write that the helium nucleus is coming in. You don't have to write that you're ejecting a proton. That's all implied here. If you're looking at an alpha particle neutron reaction, then you're doing the same basic thing like what you did up here. You just change it, or you know what the products or the what you started with and what you ended with. This is just changed from proton to a neutron. All right, so we've got proton bombardment. So the most common proton reaction consists of a proton being captured by the nucleus, and then you have the emission of a gamma ray. This is known as the proton gamma ray reaction. So examples are this. The possible reactions produced by proton bombardment are proton neutron, proton deuterion, and proton alpha particle. Deuteron, sorry, I mispronounced that. The deuteron bombardment, you can see here where you've got the deuteron coming in, then you've got a neutron that is going to be ejected. You can also see the deuteron coming in, a proton being ejected, and an important reaction that has been used as a source of high energy neutrons is the bombardment of beryllium by deuterons. And this process is known as stripping. In this process, the deuteron is not captured by the nucleus, but passes very close to it. The proton is stripped off from the deuteron, and the neutron continues to travel with high speed. So that's kind of cool. So you can see here that deuteron bombardment is a combination of proton and neutron. And this combination appears to break down in most deuteron bombardments with the compound nucleus emitting either a neutron or a proton. Since neutrons possess no electric charge, they are very effective in penetrating the nuclei and producing nuclear reactions. So you've got several different types of neutron bombardments here, and how that can change, say, a boron into a lithium. Oops, I knew I was missing something. Most common process of neutron capture is going to be the neutron gamma reaction. So the compound nucleus is raised to one of its excited states and then immediately returns to its normal state with the emission of a gamma ray. The gamma rays are called capture gamma rays, can be observed coming from a hydrogenous material such as paraffin used to slow down multiple collisions in the nuclei, the neutrons, and ultimately capture some of the slow neutrons. And you can write it in this particular fashion. You've got some other things going on here, but let's go along a little further here. Photodisintegration. We had a little discussion here. It's the interaction of a high energy photon with an atomic nucleus leading to a nuclear reaction and to the emission of one or more nucleons, which is kind of what you're seeing here. So you've got a concept here of the threshold energy, which is the difference between the rest energy of the target nucleus and that of the residual nucleus plus the emitted nucleon. Because the rest energies of many nucleon are known for very high accuracy, the photodisintegration process can be used as a basis for energy calibrations of machines producing high energy photons. So fission. Fission is produced by bombarding certain high atomic number nuclei by neutrons. The nucleus splits into nuclei of lower atomic number as well as additional neutrons. That's what it's talking about here. So you've got the plot of nuclear fission yield as a function of mass number of fission nuclei. So you can see the mass number here, see the fission yield. So you can see, roughly here, around 85, 86, up to maybe a little less than 100. You can see quite a bit of yield here. Same thing up here if you're looking at a little over 130, up to maybe about 150. Those are where you start to see a significant amount of yield. The additional neutrons released in the process may also interact with other uranium-235 nuclei that can create the possibility of a chain reaction. To induce a chain reaction, neutrons have to be slowed down to thermal energies by collision with nuclei of low Z material. It's called moderators. But a sufficient mass, or more technically the critical mass of the fissile material, is required to sustain a chain reaction. So this process has become a major energy source, as in the case of nuclear reactors. In a nuclear reactor, the chain reactions are controlled and sustained in a steady state. In a nuclear bomb, I would not use the word control to describe what happens. The chain reaction occurs in a fraction of a second, causes an explosion, and you get a place that nobody wants to live anymore. Fusion. It is the reverse of nuclear fission. Rather than taking a nucleus and pulling it apart into components, you're taking parts and you're putting them together. Just like here, if you're going to fuse a hydrogen atom into, let's see, I believe it's tritium, this is the kind of stuff that you're going to get out of it. So for this to occur, since you've got a positive Q here, it must be brought sufficiently close together so that the repulsive Coulomb forces are overcome and short-range nuclear forces can't initiate the fusion reaction. They can start pulling things together. So you can do that by heating low Z nuclei to very high temperatures. In other words, you're not going to do this on your kitchen stove. Something comparable to the inner core temperature of the sun, where none of us have really been. In practice, the fission reactions have been used for starters of fusion reactions. Sorry. And you can see what's going on here. So fission process is made self-sustaining by the chain reactions, and nuclear fuel is usually uranium-235. Here are some examples. The fuel in cylindrical rods is arranged in a lattice. The fast neutrons have to be slowed down by collisions with nuclei of low Z material. That's often why you see a lot of water in those types of plants in order to be able to cool or slow down those neutrons. These fuel rods are immersed in those moderators. And the positions of those control rods in the reactor core determine the number of neutrons available to induce fission and control the fission rate or power output. So once you've got that going on, you've got the water in here, boils to steam because of the control rods here and the energy they absorb. Steam is then pumped out, used to turn a turbine, which is hooked up to a generator, and takes the power out to people to sit there and watch their lectures in their homes about how nuclear reactors can provide them power to do that kind of thing. The problem is for these things is when the control rods are not successfully managed, and if you end up having a scene out of Chernobyl, that doesn't do a lot to the real estate value of the surrounding property. So we've got, we've got some issues there that we have to deal with regarding this. It is a source of power, can be a very nice source of power, but you got to manage it, and you got to manage it pretty well. Okay, that's the basics here. I will be working problems a little bit later, but that is the overview of the chapter.